Hello and welcome to the Massachusetts Maritime Academy Environmental Monitoring for 2021 through 2022. Group members Sergio Astarita, Vincent Fleck, Alexa Huppe, Tegan Murray, and Camryn Roberts-Capak monitored changes in Zostera marina or eelgrass density local to the Buzzards Bay area.
The purpose of our study was to monitor the seasonal changes in eelgrass density and the abiotic factors that contribute with density changes. The study area was located in northeast Buzzards Bay, which contained three smaller focuses areas of Onset Bay, Hayfield, and the Massachusetts Maritime Dock. These areas were chosen for the study because there is a known eelgrass bed, as indicated by the Massachusetts Department of Environmental Protection. With the research team based at Massachusetts Maritime Academy, this location in Buzzards Bay is an excellent site for the study because of its known ease of access and close proximity to campus. Our data was collected using a high-resolution observational data using a underwater HD video camera and GPS from a boat via a series ArcMap collectors. Changes in water temperature, salinity, water level, and light penetration were continuously recorded by situ data loggers. During the weeks of data recording and observations, which started from 4/12/2022 through 5/17/2022. So this is our second semester of our continuous study. Again, our sites consisted of Onset Bay, Hayfield, and a location about 10 meters off of the shellfish floating docks at Massachusetts Maritime Academy. And our purpose of our study happened because in the 1930s, there was a wasting disease which destroyed a large fraction of the North Atlantic populations of Zostera marina. And investigations linked this issue to nitrogen loading from underwater groundwater and sources to the growth of microalgae and the decline of Zostera marina. And in 1991, the Buzzards Bay National Estuary Program developed a comprehensive conservation plan and management plan to protect and restore habitat and living resources. Therefore, eelgrass loss was deemed a significant concern, requiring a management plan. And today, aerial photographs and GIS mapping have been key in documenting changes to the beds. And these can be used to target research in areas with increased nitrogen loading and establish critical loads.
This study was conducted aboard the 22-foot research vessel Zostera. This center console has a 150 horsepower Suzuki engine on a jack plate, allowing us to access shallow sites down to a half a meter in water depth. This jack plate was also instrumental in our project, as many of the eelgrass beds are found in shallow waters. A Simrad chart plotter was used to mark waypoints with precise buoy locations and navigate in shallow waters. The research vessel Zostera is also outfitted with an underwater Seadrop 550 HD camera. The camera is operated from a davit arm. This allows the operator to feed out a rope and cable, connecting the camera to a live video feed topside. Footage is recorded onto an HDMI H264 recorder, then transferred to a flash drive for computer upload. There are two monitors aboard, a 23-inch True TV HD screen, and a secondary 10-inch TrueView HD screen. These screens allow observers on the bow and behind the console to view the live video feed. Deploying the underwater camera for video mapping is relatively simple. First, turn on the screen next to the console to make sure the video feed is working. This should generally be done at the dock before departure, allowing the group to test connections and reconfigure if there's a problem with the video feed. Once the equipment has been tested and you've arrived at the site, a flash drive can be plugged into a port at the top of the console to record video and download it onto a computer later. The small remote provided can be used to start and stop the recording. To ensure video is being recorded, look for a solid red light to the left of the top compartment on the console. The operator can place a line in the pulley and deploy the underwater camera over the rail. The operator should feed out an equal amount of line and cable to ensure that the camera is not being supported by the cable, but there's not enough slack for the cable to become tangled. The rear-facing screen will allow the operator to see the video feed as they lower the camera. The camera should hang about a foot above the bottom for the best quality images, depending on water clarity. At each site, data points will be collected on the GTAC computer. First, an image of the substrate is captured on the underwater camera. Then a series of questions will be answered as prompted by the GTAC. First, the observer will select PI as the point type. Then, note if Zostera marina is present. If true, the observer will note the percent density, either less than 5, 5 to 25, 25 to 50, 50 to 75, or 75 to 100%. Next, the observer will look for algae present. If true, they will note the percent density and type of algae present. The observer will select the location of the point taken within the eelgrass bed, either outer, middle, or inner. Then the observer will note if epiphytes are present. If so, they will note percent density. After that, note if there is algae present, select which type, additional comments, and percent algae density. Next, they will select the kind of substrate at the site, either sand, silt and clay, or pebble and cobble. Then they will record the water depth from the boat's fathometer and additional observations. Lastly, they will note if sponge is present. After points are saved and submitted on the GTAC in the field, the data are entered into the Zostera point data collection sheet. This sheet should be included in the project report.
The individual point collection sheets are then compiled into a large table to compare Zostera density and other factors across different sites. At each station, we also fill out field data sheets, which includes general information, the tide, lux measurement, air temperature, and even observations such as the YSI salinity measurements. We then compile the data sheets into one table, which makes it easier to compare all stations on different days.
As the helmsman positions the research vessel with the buoy on the port side of the bow, 2 research members are stationed, one with a boat hook snagging the line attached to the buoy. The 2 members pull the buoy system up by hand, and with care not to scrape the cinder block anchor on the side of the vessel. Once the buoy system is safely brought onto the vessel, bow fouling is removed by hand, and data is retrieved from the 4 sensors: a Huppe water level logger, 2 Huppe pendant temperature light intensity data loggers for the top and bottom, and a Huppe saltwater conductivity salinity logger. Utilizing the Huppe waterproof shuttle and Huppe software in the computer, this data is retrieved for further analysis. A vital step while retrieving data is to check the condition of the sensors for fouling on the sensors that could interfere with accurate data collection, such as capitula on the vanadium plate of the Huppe saltwater conductivity salinity logger, or algae and other organisms growing on the other sensors.
To transfer the sensor data, we brought our laptop into the field with Huppe software downloaded. You take the protector covers off the loggers and line them up and plug them into the logger shuttle, which then transfers to the laptop. This shuttle adapter seen here is for the light intensity loggers, and there is a separate one that fits the salinity and water level loggers. We did this at each station during every field day unless rough weather left them inaccessible. To transfer the data, you will click the launch readout on the top left. You will then click Don't Stop Collecting Data. Once at 100% upload, it will give you a graph and data points. Make sure to save this to your computer. You can go in later and adjust the graph if need be. All graphs are then placed into our Google Drive and uploaded into our final report. This is a YSI water quality probe that we try to use on each given field day at each station to record salinity so we can compare it to the salinity levels obtained from the loggers. To operate the YSI, you simply remove the rubber cover from the probe and place the probe into the water, at least a few feet down. You then wait for a reading on salinity, and then we record that into our field data sheet for that day. We also measure light intensity with this lux meter that is then recorded into our field data sheet for that day. To operate the lux meter, you simply turn on the on button and hover it over the boat like so.
Once data collection is complete, the helmsman positions the vessel back to the buoy location, marked on the SIMRAD chart plotter. The buoy line is neatly coiled up, and 2 members position themselves to return the buoy to the water. One person holds the cinder block, while the other holds the coiled line and buoy to ensure no one gets caught in the line. When the helmsman confirms they are at the location, a member counts down from 3, and the buoy system is dropped back in its location.
Getting into our data analysis, there will be no data for the dock location for the spring semester due to loss of our equipment. Looking at salinity in the fall, both onset and the dock location show a large drop due to algae covering the sensors, but we did obtain the YSI measurements for those locations. Hayfield shows a relatively consistent salinity except for the drop-off that occurred during the nor'easter in November. For the spring semester, we had an issue with the onset logger. As you can see, it is saying salinity was below 1 parts per thousand, which is incorrect. Hayfield salinity is consistent around 31, with the YSI average around 31.5 parts per thousand. Salinity in the spring semester increased by about 1 parts per thousand compared to the fall semester. Looking at the water levels in the fall, you can see that onset was our deepest location and the dock being the shallowest. You can also see an overall negative trend in temperature as the winter months were approaching. In the spring, both onset and Hayfield had larger fluctuations in depth compared to the fall. There is also an increasing trend in temperature as the summer months are approaching. Onset in the fall had higher light intensity for the top sensor, and in the spring had more light intensity for the bottom sensor. This could be explained by the shallower depth this semester. Hayfield light intensity was similar for the top sensor across both semesters, and light intensity was higher in the fall for the bottom sensor.
Reflecting on this past spring semester, a total of 24 observation points were collected in the months of April and May. Observation points made in the March through May period have yielded varying average coverage of eelgrass at each site. Both Hayfield and onset locations had an average coverage of 5 to 25%, while the MMA dock location had average coverage of 25 to 50%. Epiphytes were present for a majority of the points taken, presence being true for 17 of 24 observation points. Temperature gradually rose at each site from approximately 5 degrees Celsius to 14 degrees Celsius. This limited amount of data required is the result of technical difficulties with the GPS and GTAC systems carried over from fall 2021. Additionally, the stationary buoy for the MMA dock site was lost twice from unknown causes. Thus, no in situ environmental data was collected for the MMA dock location. It is recommended to not keep stationary buoys in the water during the winter season to avoid loss of gear during inclement weather. The technical difficulties were addressed by replacing the GPS antenna, which had a corroded cable. Additionally, the GTAC tablet was replaced with a GTAC laptop. This relieved troubles with the touchscreen not functioning due to sea spray, rain, during rough conditions.
Our research was extensive, thorough, and exciting during our time on the water. But, as with any business on boats, turbulence is to be expected. We made a note of a few changes to implement within the following semester. There was a lot of technology used in the field, including a GTAC tablet that recorded our data from day to day. Because of the touchscreen, disruptions such as extreme temperatures and sea spray made it difficult to work with. In order to avoid a temperamental screen and future interruptions due to conditions of the boat, we recommend using a GTAC laptop for next semester to guarantee seamless data collecting. One of the most common errors on board was the inconsistent function of the GPS. After several attempts to reset the equipment on campus and by the manufacturer, we tested a new antenna to improve the location accuracy. We recommend implementing this new equipment in addition to the existing GPS technology for a reliable reading. We also advise revisiting previously visited points during future research in order to closely monitor the health of the grass beds. This will involve the work of past contributors and gain future perspective of grass beds across various seasons. Lastly, let's remember to review proper knot tying techniques before releasing buoys into the water for the semester. Secure all equipment with zip ties and only use reliable knots like bowlines and hitches before submitting cinder blocks underwater. We look forward to handing off our work to the next crew and wish them a positive experience contributing to this project. We acknowledge and appreciate the support of our advisor and mentor, Dr. Heffernan, and relief of Professor Hubbard and the availability of the Marine Department. We proudly represent the MSSCP Department of Mass Maritime and are grateful for this memorable opportunity. All the best and congratulations to the class of 2022.